Here is the exact question for this lesson. We have an inverting op-amp. The input signal is Vi. It passes through R1 into the minus input node. The plus input is grounded. A feedback resistor RF brings the output back to that same minus node. First, we want the general relation between V output and V input. Then, in the example, we use Vi equal to 5 volts, R1 equal to 1 kilo ohm, and RF equal to 2 kilo ohms. We will find V output and the voltage gain step by step. The central idea is virtual ground. Let us say it carefully because this is where many students get lost. The plus input is physically connected to ground, so V plus is 0 volts. With negative feedback and an ideal op-amp in its linear region, the op-amp drives its output until V minus becomes almost equal to V plus. Therefore, the minus input node is approximately 0 volts. It is not a wire to ground, but its voltage is almost 0. That is why we call it virtual ground. Now look at the current. In the ideal model, no current enters the op-amp input, so the current that comes through R1 has only one place to go, through RF toward the output. That is why the two resistor currents are equal. We write the left current as Vi minus 0 divided by R1. We write the feedback current as 0 minus V output divided by RF. Since the currents are the same, those two fractions are equal. Now solve that equation without skipping the sign. Vi over R1 equals negative V output over RF. Multiply both sides by RF. RF over R1 times Vi equals negative V output. Move the minus sign to the other side, and we get V output equals negative RF over R1 times V input. The voltage gain is therefore AV equals V output over V input, which is negative RF over R1. The minus sign is the inversion. Now plug in the numbers from the example. RF over R1 is 2 kilo ohms divided by 1 kilo ohm. The kilo units cancel, so the ratio is 2. Therefore, V output equals negative 2 times V input. If V input is 5 volts, then V output is negative 10 volts. Equivalently, the input current is 5 volts divided by 1 kilo ohm, which is 5 milliamps. The same 5 milliamps through 2 kilo ohms gives 10 volts across RF, and the output side must be negative. Before we accept the answer, check the supply rails. The op-amp is powered from plus 12 volts and minus 12 volts. Our calculated output amplitude is 10 volts. 10 volts is inside the 12-volt limit, so the ideal result is possible here. If the calculation had asked for, say, 15 volts, the real output would clip near the rail. In this example, negative 10 volts is safe. What does that mean for the sine wave? The frequency does not change. It is still 1 kilohertz. The amplitude doubles because the magnitude of the gain is 2, but the minus sign flips the waveform. So when the input is positive, the output is negative. When the input is negative, the output is positive. In short, V output is an inverted sine wave with twice the amplitude of V input. The inverting op-amp is one of the most important op-amp patterns. Read it with 3 ideas. First, the plus input is grounded. Second, negative feedback makes the minus node a virtual ground. Third, because op-amp input current is 0, the current through R1 must continue through RF. From those 3 ideas, the formula follows naturally. V output equals negative RF over R1 times V input. For this example, the gain is negative 2 and the output is negative 10 volts for a 5-volt input.